Hello guys, today we'll be talking about vectors. And before we dive into the whole concept of vectors, let us examine two important terms. We have what are called vector quantities and we have what are called scalar quantities. A scalar quantity is a quantity that has magnitude only, while a vector quantity is a quantity that has both magnitude and direction. An example of a scalar quantity is mass. And mass is basically your composition, how much matter you contain, while its corresponding vector quantity is what we call weight. Now, weight is influenced by gravity. So, for instance, if I'm on the moon where the gravity is less, my weight will be less. But if I'm on Earth where the gravity is more, my weight will be more. And gravity acts downwards. So, for instance, let us say you're standing here. At some point above the ground, the gravity will pull you downwards. So there we have the direction that force is acting. And we normally say that weight is equal to mass times gravity, right? And weight acts downward. Mass is just your composition. How much matter does your body contain? Another example that we could compare is what we call distance, which is scalar, and we could compare this to displacement, which is a vector quantity. Let us say, for instance, your mom sent you to the shop. However, you live right here. The shop is right here. However, to get to the shop, you probably have to walk. The road is in this direction, so you probably have to walk 10 meters in this direction, and then you have 2 meters in that direction. So, in all, the distance you'd have walked is actually equal to 12 meters. That is my distance, and that is scalar. What displacement does is look at where the shop is relative to where you started. So while my distance is 12 meters, looking at where I started here, and looking at where the shop is, I'm going to put my displacement here in red so you can see it. My displacement would have been this. Alright, so it looks at where you are relative to where you end. And that distance right there is really a straight line right there from where you started to where you ended. So the direction, this is not specified direction, and that is what is important. However, your distance would still be 12 meters. For those of us who like to play games, we employ the use of vectors a lot. Here we have a simulation, and this simulation is done by FET, that Colorado. It's an educational site where you can look at projectiles and so on. Now here we have a cannon, and we have a target that is 15 meters away. Now my aim is to hit this target. If you look over here, we have to give this ball an initial speed. Now we can adjust the speed. Right? Now the speed is not the only important thing. While I'm going to show this cannon with a given speed, the direction will be important. So for instance, let us leave the cannon as it is, and let us attempt to fire and see what happens. So we fire first, and look what happens. I would have missed my target because I did not specify the direction. I didn't give it a direction that would allow it to hit my target. So we can keep this 20 meters per second, but by changing this angle right here, we can adjust the direction of this cannon. So let us see what happens. Let us adjust this angle and see what happens. Alright, so now I'm at 60 degrees. My initial speed is 20 meters per second, as before. In this case, I still miss the target, which means I need to adjust the angle here, which will ultimately adjust the direction that the cannon is fired. So probably we could increase the angle a bit. Let us say we put it at 70 degrees and see what happens. Still have an initial speed of 20 meters per second. Whoa, and we almost hit the target. So we probably need a larger, or we need a smaller angle. Let's go with smaller and see what happens. Fire again. And this time, well, we almost hit the target, so probably a little adjustment here. So you can see how important my direction here is. Let's go again. We're now at 65 degrees and going down. Still need a next angle. Probably I could put it at a slightly larger angle. Let me go see if I can get 67 degrees. All right, adjusting. It would appear my angle is a multiple of 5. So let us adjust the initial speed and see what happens. Alright, so it's now at 19 meters per second. Fire. Whoa, and I hit my target. Now we're going to introduce some vectors so you can actually see the different directions in which this is going. Because notice that the ball is moving upward and it's moving forward. But at each point, the direction is constantly changing. So let us fire again and show you what happens. Look at those vectors there. Look at how the ball is moving. You can see that each time the direction is changing. So we had an initial speed of 19 meters per second, and at an angle of 65 degrees, we hit the target. All right, so you can see how important the magnitude here, which is my 19, which is an initial speed that I gave it, and the angle here plays a critical role as well. All right, now let us look at how we represent a vector. Now, a vector can generally be represented using a common letter, and is normally written in this form. So u equal xy. Now, in this case, this is what is referred to as a column vector. All right. Now, u is said to be a free vector because it's just a random vector in space. Now, apart from using u equal xy, we can also put this in a different form, the form we call the ij form. And of course, this is vectors in the two-dimensional plane. So I could also represent this vector as u equal xi plus yj. Now I is a unit vector in the horizontal direction and j is a unit vector in the vertical direction. And bear in mind what we said. We said that these are free vectors, which means they are just random vectors in space. However, I could present a vector that let us use the same vector as AP. What AP means is that the vector is going from A to P. And notice the arrow above the AP, which tells me that I'm going from A, I'm starting at A, and I'm ending at P. Now, this is called a displacement vector because this is telling me where I'm going from one place to another, or where one place is with respect to another. It is written in the same way, so I could still put it in the column form, which is xy, like that, or I could go AP equal xi plus yj. Now, normally when we use a common letter, we say it represents a free vector, which means it can be anywhere in space. So if I were to represent this on a Cartesian plane, it means that I could practically put it anywhere. So let's take an example. So for instance, let us say that u was equal to 4 minus 6. What does this actually mean? It means that I'm moving 4 places horizontally and 6 places vertically. But here, of course, direction is important. We know once a number is positive, we normally go to the right if we're moving horizontally. And if it is negative, we normally go down if we're moving vertically. Now let us take this over to the Cartesian plane and see what actually happens with this free vector. For my Cartesian plane, I will be using the GeoGebra software. So we'll go over here and let us choose a vector. Bear in mind that our vector was 4, negative 6. So this is my vector over here. And because this is a free vector, we can practically start at any point. We create our own starting points. So let us say I want to put the vector right here. Now, the 4 means that I'm going 4 places to the right, and the 4 is positive. So we go 1, 2, 3, 4. It means also the negative 6 means that we're going 4 places down because the 6 is negative, so we count 6 places down. So we have 1, 2, 3, 4, 5, 6. So my vector ends here. So if you look over to the left here, we have 4, negative 6. Now what GeoGebra does is to put the arrow at the end. But to make this diagram look neater, what you could do when using your graph paper is to put the arrow in the center, like probably where the U here is. And because this is a free vector, I'm simply just going to remove the A and the B. Now, before I remove A and B, let us look at the vector again. Alright, so you see what would be the difference between a free vector, which would be U, and a displacement vector, which is AB. AB, as a displacement vector, tell me that this vector starts at A, and it ends at B down here. U being a free vector tells me that this vector can be anywhere in space. So to show that this is a truly a displacement, a free vector, sorry, let us remove A and B. So there we go. That is my free vector. And notice that I obtain this vector by simply counting. As we go back again, the 4, which means I move into 4 places horizontally, means that I have to go 4 places to the right because that 4 is positive. So we went 1, 2, 3, 4. The -6, which refers to my vertical movement, 6 is negative, so it means that I have to go 6 places downward. So we went 1, 2, 3, 4, 5, 6. And that is how we got this vector here. We're now going to be looking at what we call a negative vector or negative vectors. Let us go back to u. U is equal to 4 minus 6. What this means is that I'm going 4 places to the right and 6 places down. Now a negative vector, which is the opposite of this, I'm going to be reversing this process to see what happens. Alright, so I'm changing direction. So my negative vector would actually be represented as negative u. So I would have minus u. Now, if I were to reverse this process, going 4 places to the right, the opposite of that would be going 4 places to the left, which means that I'm gonna, so let me first start by putting the minus sign here. So we have 4 minus 6. So now I need to go 4 places to the left. So when I simplify this, it's gonna become minus 4. And the minus 6 meant I was going what, 6 places downward. And then the opposite, of course, would be to go 6 places upwards. So when I negate that, the signs of the terms inside will change. So I'm going to end up with a positive 6. So I'm going 4 places to the left now, and I'm going 6 places upward when I negate this vector. And let us go to the Cartesian plane and look to see what would happen in this particular scenario. Let us pick a random place to put this vector. So we say we're going 4 places to the left. So let us say we're starting right here. So we're going to count 1, 2, 3, 4. 4 places to the left. And we're going 6 places upward. So we have 1, 2, 3, 4, 5, 6. And there we go. That's my negative vector. Now I'm going to rename this vector. Now for the meantime, we're going to call the negative vector vector v. Now look at both vectors. The only thing that practically changed when I negated the vector is the direction. It's going in the opposite direction. Now how can I prove that? Let us try to move vector v to see what happens. So let me pull over vector v. If I pull vector v over, it superimposes on vector u, which was the original vector. Bear in mind that vector v is a negative vector of u. So you see how important direction is. Because while this is a negative vector, everything seems to be the same apart from the direction in which I'm going. And of course, bear in mind we told you that the direction is shown by the arrow. And of course, for a Cartesian plane, we can simply put this arrow in the center of the vector. So by negating the vector, all we change is the direction of the vector. Everything else remains the same. We're now going to look at what we call position vectors. But to bring out this concept, we're going to examine 2 points on the Cartesian plane. Points, we also call them coordinates. So let's say we have A, which is 4, 2, and we have B, which is -6, 3. We're going to put these 2 points on my Cartesian plane. Now, let us look for point A, which is 4, 2. 4, 2 generally means 4 on the x-axis and 2 on the y-axis. Those 2 points would intersect right here. So that is point A. Point B was -6, 3. So let me come back here. So I'm looking for -6 on the x-axis and 3 on the y-axis. So we have points A and we have points B. Now, generally, whenever you plot a point, you plot it relative to what we call the origin. And generally, we use a capital O to represent the origin, but we don't put that on the Cartesian plane. But we know that this point where the 2 axes intersect is what we call the origin. So when I plotted point A, which is 4, 2, what it really means is that I went 1, 2, 3, 4 places horizontally to the right, and I went 1, 2, 2 places up, which is a vertical movement. So it means now that I can turn point A into a vector because it's coming from the origin, and I would have moved 4 places to the right and 2 places up. Now, because it's coming from the origin, it is what is referred to as a position vector. Similarly, for point B, whose coordinate is -6, 3, it really means that I went 6 places to the left, and I went 3 places upward. Now, of course, this was plotted again with respect to the origin. So again, we call it a position vector. So let us put in the vectors and see what happens. So both points come from the origin. So let us start my vector here at the origin and go up to point A. And I go again from the origin up to point B. Now, to confirm this, let us count off the vector. Bear in mind that your coordinate was 4, 2. Let us see what happens with the vector. We go 1, 2, 3, 4 places to the right, 1, 2 places upward. So we actually got the same thing as the coordinate in terms of looking at the movement here. But bear in mind that a coordinate is represented in this form, as you can see at the top left hand corner here, 4, 2. But as a vector, we have to go the column form or we go the ij form. So all points that we put on a Cartesian plane technically can be represented as a position vector. So let's go back and do that manually. So as we demonstrated on the Cartesian plane, a position vector is a vector that starts from the origin. So let's put that somewhere here. Now my coordinates here are A 4, 2 and B -6, 3. Now we say because these are taken with respect to the origin, they can be represented as position vector. So all coordinates can be represented as position vector. Now to put this in vector form, because we start from the origin, we're going to have O, A. So we start from the origin and we go to A. So as a vector or as a position vector, this becomes 4, 2. Similarly for B, B is a coordinate in this form, so we have -6, 3. But B is represented with respect to the origin, and therefore B can be represented as a position vector. And we're going to have it as OB with R above equal -6, 3.